So now we're just going to work through some examples here of using integration by substitution. So you're going to note that every time I do one of these, I start by just asking myself, do I know of a function that has this derivative to begin with? Because even though we are doing a lot of integration by substitution, it is not as common to use as just knowing the antiderivative directly. So here I have the integral of x plus 1 times the quantity of x squared plus 2x minus 3 squared. I don't know of any function that has that as its derivative. So I need to say what u is equal to. So u is equal to, I want it to be the inside. Well, I see two different insides, x plus 1 and the x squared plus 2x minus 3. Because the x squared plus 2x minus 3 is squared, it's the inside of a power. That's a good place to start. I don't know if it's going to work, but it's a nice place for us to start. If it doesn't, I'll come back and try x plus 1 instead. But then I need the du dx. So that's 2x plus 2. And then solve that for dx. 1 over 2x plus 2 du. So now I want to do substitution here. So I don't have anything to substitute for the x plus 1, so it stays there. The x squared plus 2x minus 3 becomes u squared. And the dx becomes 1 over 2x plus 2 du. Now, at first glance, this looks like a bad substitution because I still see x's there. But what I want to see is, will these x's cancel at this point? So I notice that 2x plus 2 is the same as 2 times the quantity x plus 1. And then my x plus 1's cancel. And what I'm left with is 1/2 the integral of u squared du. There are no x's left, so this is a good substitution. So I have 1/2. The antiderivative of u squared is 1/3 u cubed plus c, because it's an indefinite integral. And then I need to replace my u with what I said it was equal to at the beginning. And here is my antiderivative. If I look at my next example here, the square integral of the square root of 4x plus 1, radicals are unfriendly to us in calculus, so I'm going to change that to an exponent. I don't know of anything that has the square root of 4x plus 1 as its derivative, so I'm going to try substitution. So I want u to equal the inside. So we're going to try 4x plus 1 and see if that works. Find du dx. Solve for dx. I can then do my substitution. Replace the 4x plus 1 with a u. And dx is being replaced with 1/4 du. No x's are left, so this looks like a good substitution. So I can start working on my antiderivative. 1/4 is a constant multiple. Antiderivative of u to the 1/2 would be 2/3 u to the 3/2 plus c. And then change the u back in terms of x's, because I was asked for this with respect to x. So I'm going to have 1/3 quantity 4x plus 1 to the 3/2 plus c. And there's my antiderivative. If I then go to some other ones, trig is where these tend to get a little bit tricky. So you're going to see I've got several trig examples to go with this. For the tangent of x, I don't know of anything that has the derivative of the tangent of x, and it doesn't look like there's anything for me to say inside. But if I change tangent into sines and cosines, tangent is the same as sine over cosine. Again, I do not know anything that has sine of x over cosine of x as its derivative, so I'm going to try substitution. A good place to start with a fraction is the denominator. So u is equal to the cosine of x. So du dx is equal to negative sine of x. And dx is equal to negative 1 over the sine of x du. So nothing's nothing replaces my sine of x. Cosine of x is replaced by u. Dx is replaced by -1 over the sine of x du. And I can now see that sine of x is going to cancel sine of x. So I have the negative integral of 1 over u du. I can evaluate that. So I have the negative antiderivative of 1 over u is the natural log. I need to guarantee that u is positive because nothing has told me that u is positive. So I do need my absolute values to force it so that I'm able to take the natural log of u. And then plus c. And then I'm asked for it in terms of x. So it's the negative natural log of the absolute value of the cosine of x plus c. This is not what people think of when they think of what has a derivative of just tangent, but this is, if I take this derivative, I do end up with sine over cosine, which is tangent. If I then look at my next example here, the integral of 5x to the fourth times secant squared x to the fifth, it can sometimes be tough to see what to do here because I have several insides. I have 5x to the fourth is inside of a parentheses. I have x to the fifth is inside of secant, but then secant is inside of squaring. My recommendation is always try to go for the most inside. But this is one that would typically, especially as you're right now learning about integration by substitution, this is one that there's probably going to be some trying to do. I'm leaning towards x to the fifth because I already know one step ahead its derivative is 5x to the fourth. So I'm going to try x to the fifth. Du dx is equal to 5x to the fourth. So dx is equal to 1 over 5x to the fourth du. So when I do my substitution, nothing has replaced 5x to the fourth. I still have my secant squared, but now it's of u. And then dx is replaced by 1 over 5x to the fourth du. So the 5x to the fourths cancel. I'm left with just the integral of the secant squared of u, which would be tangent of u plus c, which is the tangent of x to the fifth plus c. For these, give these two a try, pause the video, give them a try, and then come back and see if you did them correctly. Again, just pause the video. After you've tried these two, come back and check your work. So here, I've got sine, I've got cosine. They're both derivatives of each other, but sine is inside of to the fourth power. It may help you to think of this as the integral of sine of x raised to the fourth cosine of x dx, written like this to make it easier to see the inside. So I'm going to say u is equal to sine. Again, this might work, it might not. Derivative with respect to x would be cosine of x. So dx is 1 over cosine of x du. So I have the integral of u to the fourth. Nothing has replaced cosine of x. Dx gets replaced by 1 over cosine of x du. So my cosine of x's both cancel. I'm left with the integral of u to the fourth du, which would be 1/5 u to the fifth plus c. Change back to x's, so I have 1/5 sine to the fifth plus c. Here, I don't know anything off the top of my head that gives me a derivative of 1 over cosine squared. So I am tempted to say, well, what about saying u is equal to cosine of x? So du dx is equal to negative sine of x. Dx is equal to -1 over sine of x du. So I'd have the integral of 1 over u squared times -1 over sine of x du. But now I have a problem. And what I can see here is that not all of my x's cancel. Nothing cancels that sine of x, so this is a bad substitution. Cosine's not going to work. And if I try cosine squared, same thing. What happens here is this is not actually a substitution problem. 1 over cosine squared is the same as secant squared. I actually do know how to do this one directly, because the antiderivative of secant squared is the tangent of x plus c.